Hello there, and welcome. If you found your way here tonight, perhaps your mind has been wandering, thinking about mysteries, about vast unknowns. Or maybe you're simply ready to let the day drift away. Either way, you're in the right place. Let your shoulders soften, your breathing slow down just a little, and allow yourself to settle in. There's nothing you need to do but listen and rest. Tonight we're going to drift through a different kind of story, not one filled with action or urgency, but one that unfolds gently across centuries. A story about humanity's patient, persistent desire to understand what lies beneath the waves. Did you know that for most of human history, the deep ocean was more mysterious than the stars above? Even today, we've mapped more of the moon's surface than our own ocean floors. In this quiet journey, you'll hear about curious minds who lowered weighted ropes into darkness, about vessels that descended where sunlight never reaches, and about discoveries that changed everything we thought we knew. We'll travel from the earliest attempts to measure ocean depth, through the first scientific expeditions that revealed life in the abyss, to the modern robots that now explore valleys deeper than mountains are tall. Each step forward came slowly, carefully, driven by wonder rather than haste. But before we jump in, if you enjoy learning about our oceans, you're welcome to let us know where you're tuning in from and what time it is for you. It's always fascinating to see how far our stories reach. And if these quiet ocean journeys help you unwind, you're always welcome to subscribe so you can drift off with us whenever you need. Now let your body grow a little heavier as we begin. Long before submarines or diving suits, before any human had descended more than a few meters below the surface, the ocean held a special kind of mystery. It was always there, vast and visible, yet entirely unknowable beyond its surface. The ancients watched waves roll in from horizons they could barely reach, and they wondered what lived in those depths. How deep did the water go? Did the seafloor mirror the land, or was it something entirely different? The earliest attempts to understand the ocean were simple, practical efforts. Fishermen learned the rhythms of tides and currents not from science but from necessity. They read the water's color, felt the pull of unseen forces on their nets, and passed down knowledge through generations. But actual exploration, the deliberate investigation of what lay beneath, remained beyond reach. The ocean was a barrier, a surface that could not be crossed downward without suffocating in its cold embrace. In the 8th century, Viking sailors began measuring ocean depth in the simplest way imaginable. They dropped lead weights attached to ropes over the side of their ships and counted how much rope disappeared into the water before hitting bottom. This method, called sounding, was crude but effective in shallow waters. It told them where sandbars lurked, where harbors deepened, where ships could safely anchor. But in the open ocean, where the seafloor plunged thousands of meters down, their ropes were far too short. The deep ocean remained unmeasured, a vertical wilderness beyond the reach of rope and stone. As centuries passed, maritime nations began to see the ocean not just as a highway for trade, but as a subject worth studying. The great age of exploration in the 15th and 16th centuries sent ships around the world, charting coastlines and claiming new territories. Yet even as explorers mapped entire continents, the water beneath their hulls remained largely unknown. They sailed over trenches deeper than any mountain, over underwater ranges and vast plains without realizing any of it existed. In the early 1800s, scientists began to ask more systematic questions. Could life exist in the deep sea? What was the ocean floor made of? How did water temperature change with depth? These questions were not just academic curiosities. Nations were beginning to lay telegraph cables across the ocean floor, linking continents through copper wires stretched across thousands of miles of seabed. To do this safely and effectively, they needed to know the contours of that hidden landscape. They needed maps of a world no one had ever seen. The challenge was immense. Water pressure increases dramatically with depth. At just 10 meters down, the pressure is double what it is at the surface. At 100 meters, it's 10 times greater. At 1,000 meters, it's a crushing 100 atmospheres, enough to compress air tanks into uselessness and collapse the lungs of any diver who tried to descend without protection. The deep ocean was not merely hidden. It was hostile to human presence in ways that altitude never was. You could climb a mountain with determination and warm clothing, but descending into the deep required entirely new technologies, new ways of thinking about pressure, buoyancy, and survival. Still, The desire to know persisted. In the early 19th century, scientists like Pierre-Sémon Laplace attempted to calculate the ocean's depth using indirect methods. Laplace studied tidal movements on opposite sides of the Atlantic, observing how the moon's gravity pulled at the water. By analyzing these tidal patterns, he estimated the ocean's average depth. His calculations were rough, based more on theory than observation, but they represented a shift in thinking. The ocean was no longer just a surface to cross, but a volume to understand, a three-dimensional space with structure and variation. Around the same time, naturalists began to wonder about life in the depths. Edward Forbes, a British naturalist, proposed in the mid-1800s that life could not exist below about 300 fathoms, or roughly 1,800 feet. He called this the azoic zone, a lifeless layer of water too cold, too dark, and too pressurized for any living thing. Forbes based his theory on the fact that most marine life he had studied lived near the surface, where sunlight penetrated and warmth was abundant. The deep, he reasoned, must be a barren desert, devoid of the energy needed to sustain life. It was a plausible theory, and many scientists accepted it. After all, no one had evidence to the contrary. No one had seen the deep ocean firsthand. No one had brought up samples of life from those depths. Forbes's azoic hypothesis seemed to fit what little was known, but it was wrong, and the journey to prove it wrong would take decades of patient, painstaking work by explorers who refused to accept that any part of Earth could be truly lifeless. The tools for deep ocean exploration were slowly taking shape. Engineers developed stronger, longer-sounding lines that could reach farther down. They attached thermometers to these lines, measuring water temperature at different depths and discovering that the ocean was layered with warm surface water sitting atop colder, denser layers below. They collected sediment samples from the seafloor, pulling up mud, sand, and sometimes fragments of rock that hinted at underwater landscapes far more complex than anyone had imagined. In the mid-1800s, the United States Coast Survey conducted systematic soundings along the continental shelf, the relatively shallow underwater extension of the North American continent. They discovered that the seafloor was not a gentle slope, but a varied terrain with sudden drops, underwater valleys, and features that seemed to mirror the land above. One officer, James Alden, found a deep submarine valley in the center of Monterey Bay off the coast of California. This canyon, now known as the Monterey Canyon, plunges thousands of feet below the surface, deeper than the Grand Canyon, yet it was entirely invisible from above. These discoveries hinted at a hidden world, a seafloor full of mountains, valleys, and plains just like the continents. But seeing that world, truly observing it, would require more than ropes and weights. It would require vessels that could descend into the pressure, carry instruments and observers, and return safely to the surface. It would require a revolution in engineering and a willingness to risk lives in pursuit of knowledge. The dream of exploring the deep was growing stronger. Every new measurement, every unexpected discovery, every sample pulled up from the darkness added to the sense that something extraordinary waited below. The ocean was not empty. It was not uniform. It was a place of variation and complexity, and possibly, despite Edward Forbes' confident predictions, it was a place where life persisted even in the most extreme conditions. By the middle of the 19th century, the groundwork for deep ocean exploration had been laid, but the real work was just beginning. Scientists had theories, nations had economic interests, and a few intrepid researchers were willing to put those theories to the test. What they needed was an organized effort, a systematic approach that could gather data from across the world's oceans, not just scattered measurements from coastal waters or convenient harbors. The Industrial Revolution had transformed what was possible. Ships were larger, stronger, and equipped with steam engines that could power through currents and storms. Laboratories could be built aboard vessels, allowing scientists to analyze samples immediately rather than waiting months to return to shore. Wire rope, far stronger and lighter than hemp, could be spooled out for miles, reaching depths that would have been impossible just decades earlier. The tools were ready. What was needed now was the vision to use them. In 1872, that vision became reality. The British Royal Society, with support from the government, launched an expedition unlike any before it. The mission was not to discover new lands or claim territories. It was purely scientific, designed to explore the ocean itself, to gather data on temperatures, currents, chemistry, and life at all depths and in all regions. It was a monumental undertaking, ambitious in scope and rigorous in method. For this purpose, the Royal Navy provided a ship, a wooden corvette originally built for war but now converted for science. Most of its guns were removed to make room for laboratories, sampling equipment, and storage for the thousands of specimens the expedition hoped to collect. The ship was fitted with miles of rope and cable, dredges for scraping the seafloor, thermometers designed to withstand pressure, and jars and preservatives for storing whatever strange creatures might be found. This ship was the HMS Challenger, and the expedition it carried would become one of the most important scientific journeys in history. It would circumnavigate the globe, stopping at hundreds of locations to take measurements, collect samples, and document the ocean in unprecedented detail. The voyage would last 3.5 years, cover nearly 70,000 nautical miles, and transform humanity's understanding of the sea. Leading the scientific team was Charles Wyville Thomson, a Scottish naturalist who had spent years studying marine life. Thomson was convinced that life existed in the deep ocean, despite Forbes' azoic hypothesis. He had participated in earlier expeditions aboard ships like the HMS Lightning and HMS Porcupine, where dredgers had pulled up living creatures from depths well beyond Forbes' theoretical limit. Clams, corals, sponges, and other animals had been found thriving in cold, dark waters, proving that the deep was not lifeless after all. Thomson knew that isolated findings were not enough. To truly understand the ocean, they needed comprehensive data from every ocean basin, from the tropics to the polar regions, from shallow coastal waters to the deepest trenches. The Challenger expedition was designed to provide that data. On December 7, 1872, the Challenger departed from Portsmouth, England. On board were nearly 250 men, sailors, engineers, officers, and 6 civilian scientists, whom the crew nicknamed the Scientifics. The atmosphere was a mixture of excitement and uncertainty. No one had attempted anything like this before. No one knew what they would find, or even if the equipment would hold up under the strain of constant use in harsh conditions. The first leg of the journey took them south toward Gibraltar, then across the Atlantic. At each station, a carefully chosen location where measurements would be taken, the ship would stop. The crew would lower sounding lines to measure depth, thermometers to record temperature, and bottles to collect water samples. They would deploy dredges, heavy metal frames with nets attached, dragging them across the seafloor to scoop up sediment and anything living on or in it. This process was slow, labor-intensive work. Lowering a dredge several miles down, dragging it along the bottom, and hauling it back up could take an entire day. The weight of the rope alone was enormous, and if the dredge snagged on rocks or underwater obstructions, it could snap the line, losing the equipment and forcing the crew to build a replacement. But the scientists were patient. They understood that this work, tedious as it was building a foundation of knowledge that would last for generations. As the expedition continued, the findings began to accumulate. The ocean floor was not a flat, featureless plain. It had ridges, valleys, and sudden drops. There were areas covered in fine clay, others scattered with gravel, and still others with strange nodules of metal, later identified as polymetallic nodules rich in manganese iron and other minerals. These nodules, about the size of potatoes, were unlike anything found on land, and their discovery hinted at chemical processes occurring deep beneath the waves. The temperature data revealed layering in the ocean, with distinct zones of warm and cold water. Surface waters in the tropics were warm, but just a few hundred meters down, temperatures dropped dramatically. Below a certain depth, the water was consistently cold, near freezing, regardless of latitude. This suggested that deep ocean currents flowed from polar regions toward the equator, carrying cold water beneath the warmer surface layers. It was the first clear evidence of a global ocean circulation system, a conveyor belt of currents that moved water, heat, and nutrients around the planet. But the most exciting discoveries were the living creatures. At nearly every station, the dredges brought up life. Sometimes it was familiar, species similar to those found in shallow waters, but often it was strange, bizarre even, adapted to conditions that seemed impossible to survive. There were fish with enormous eyes to capture every photon of faint light filtering down from above. There were worms living in tubes, crustaceans scavenging on the seafloor, and jellyfish drifting through the water column at depths where pressure would crush a human instantly. Thomson and his team carefully preserved these specimens in jars of alcohol. labeled them with the location and depth where they were found, and packed them for the long journey home. By the end of the expedition, they had collected over 4,700 previously unknown species. It was an astonishing number, proof that the deep ocean was not a desert but a thriving, diverse ecosystem. The Challenger also made a discovery that would echo through history. In the western Pacific, near the Mariana Islands, they lowered their sounding line and measured a depth of over 26,000 feet, more than 4.5 miles straight down. This was the deepest point anyone had ever measured, a chasm in the seafloor that seemed almost incomprehensible. Later measurements would refine this figure, and the depression would be named Challenger Deep in honor of the ship and its crew. For 3.5 years, the Challenger sailed on, crossing the Atlantic, the Pacific, the Indian Ocean, and the Southern Ocean near Antarctica. The crew endured storms, equipment failures, illness, and the monotony of long days at sea. One scientist, Rudolf von Willemoes, died during the voyage, a reminder of the risks involved in such an endeavor. But the work continued. The data accumulated, the specimens were preserved. When the Challenger finally returned to England in May of 1876, it brought back a treasure trove of information, but the voyage itself was only the beginning. The real work of analyzing the data, identifying the species, and writing up the results would take another 2 decades. Thomson supervised the initial stages of this massive project, but he died in 1882 before it was finished. His colleague John Murray took over, eventually publishing 50 volumes of reports, each one a detailed analysis of the findings. The complete set totaled nearly 30,000 pages, a monumental scientific achievement. The Challenger expedition established oceanography as a legitimate scientific discipline. It proved that the ocean was far more complex and full of life than anyone had imagined. It showed that systematic exploration could yield discoveries beyond the wildest predictions, and it inspired other nations to mount their own expeditions, to build their own research vessels, and to continue the work of exploring the vast, mysterious world beneath the waves. The Challenger expedition stands as a turning point, a moment when humanity shifted from speculation to observation, from myths about the sea to rigorous scientific inquiry. But the journey itself, the day-to-day reality of what the crew and scientists experienced, reveals much about the patience and determination required to explore the unknown. Imagine the scene, a wooden ship, just over 200 feet long, bobbing in the open ocean far from any land. The sails are furled, the engines idle, the crew is busy preparing equipment, lowering instruments over the side on cables that seem impossibly thin for the task they must perform. The scientists stand on deck, notebooks in hand, watching the cable unspool meter by meter, disappearing into blue-green water that fades to blackness below. The process of taking a single depth sounding could consume an entire day. First, the crew had to lower the sounding line, a heavy rope or wire with a weight attached. As it descended, they measured out the line carefully, marking each 100 fathoms. The deeper they went, the slower the process became. The weight of the line itself created drag, making it harder to tell when the weight had actually hit bottom. Sometimes they misjudged, thinking they had reached the seafloor when the line had only slackened due to currents. Once the depth was measured, they would lower other instruments, thermometers encased in protective metal tubes, water bottles that could be triggered to snap shut at specific depths, and dredges designed to scrape along the bottom and capture whatever lay there. Each piece of equipment had to be carefully monitored. If a thermometer cracked under pressure, the reading was useless. If a water bottle leaked, the sample was contaminated. If the dredge snagged on rocks, the entire apparatus could be lost. When the dredge finally came back up, often after hours of hauling on the winch, the scientists would gather around eagerly. What emerged was often disappointing: mud, sand, broken shells. But sometimes the dredge held wonders: living sponges, their bodies filtering nutrients from the water; delicate corals, their skeletons built from calcium drawn from seawater over decades; fish unlike anything in the zoology textbooks, with translucent bodies, bioluminescent organs, and adaptations that seemed designed by an alien intelligence. Thomson and his team worked quickly to preserve these specimens before they deteriorated. They sketched them, measured them, described their colors and textures while the creatures were still fresh. Then they placed them in jars of alcohol or formalin, labeled them meticulously with the station number, depth, and date, and stored them in the ship's hold. The collection grew with every stop, filling cabinets and shelves until the ship resembled a floating natural history museum. The Challenger visited hundreds of stations, each one chosen to provide a different perspective on the ocean. They sampled near volcanic islands, where the seafloor was young and rocky. They dredged in the middle of vast ocean basins, where fine sediment accumulated grain by grain over millions of years. They worked near the equator, where warm water teemed with life, and in the Southern Ocean, where icebergs drifted and the water was so cold it seemed to burn. One of the most significant findings was the sheer variety of ocean floor sediments. In some areas, the seafloor was covered in a soft, white ooze made of the microscopic shells of tiny organisms called foraminifera. These creatures lived near the surface, and when they died, their shells drifted down like snow, accumulating in thick layers on the bottom. In other regions, the sediment was red clay, fine particles carried by currents and deposited slowly over eons. And in certain spots, they found those strange metallic nodules lying scattered on the seafloor like forgotten treasures. The Challenger also encountered the challenges of working in the polar regions. As they sailed south toward Antarctica, the water temperature dropped and icebergs became a constant hazard. The ship never reached the Antarctic continent itself, but it sailed close enough to take photographs of icebergs, some of the first such images ever captured. These frozen giants, glowing pale blue and white against the dark ocean, were a reminder of the planet's diversity, of the way ice shaped the sea just as much as rock and sand. Throughout the voyage, the scientists maintained detailed logs. They recorded air temperature, sea temperature, barometric pressure, wind speed and direction, and the appearance of the sky. They noted the behavior of birds and marine mammals, the color and clarity of the water, and any unusual phenomena they observed. This wealth of data, seemingly mundane, would prove invaluable to future researchers trying to understand ocean currents, weather patterns, and climate. The crew, meanwhile, dealt with the physical demands of the work, hauling heavy equipment in all weather. Maintaining the ship and enduring months at sea without sight of land took a toll. Yet morale remained relatively high. The officers and scientists got along well, and the sense of participating in something historic sustained them through the difficult moments. When the Challenger crossed the Pacific, they spent weeks out of sight of land, dredging and sampling in some of the most remote waters on Earth. They discovered seamounts, underwater mountains that rose thousands of feet from the seafloor but never broke the surface. They found trenches that plunged deeper than any mountain on land was tall. They mapped currents, traced the boundaries between warm and cold water masses, and began to piece together the first comprehensive picture of the Pacific's vast interior. In the western Pacific, near Guam and the Mariana Islands, they took the sounding that would define one of the ocean's most famous features. The line went down and down and down, eventually reaching a depth of over 26,000 feet. It was an almost incomprehensible distance, a vertical drop into darkness that exceeded the height of Mount Everest. The scientists realized they had found one of the deepest places on Earth, a trench carved into the seafloor by the slow collision of tectonic plates. They called it the Challenger Deep, and it remains to this day the deepest known point in the ocean. As the expedition neared its end, the ship turned toward home, crossing the Indian Ocean and rounding the southern tip of Africa. The final stations were bittersweet. The crew was exhausted, eager to return to their families, but also aware that this voyage, this extraordinary journey, was coming to a close. When the Challenger finally docked in England in May of 1876, the reception was warm but not spectacular. The public did not fully grasp what had been accomplished, but the scientific community understood. This was a watershed moment, the beginning of a new era in the study of the ocean. The legacy of the Challenger expedition extended far beyond the voyage itself. The data collected provided a baseline for understanding the ocean, a snapshot of conditions before the industrial age fully transformed the planet. Modern researchers still reference Challenger's findings, comparing them to current measurements to track changes in temperature, chemistry, and marine life. The specimens, too, remain valuable. Many of the creatures collected on that voyage are still housed in museums, available for study by new generations of scientists. Some of those species have never been seen again, hinting at how much of the ocean remains unexplored even now. The Challenger proved that the deep ocean was full of life, but it also showed how vast and varied that life was, and how much more there was to discover. The Challenger expedition had proven that life existed in the deep ocean and that the seafloor was a complex landscape worth studying. But the expedition's scientists never actually saw the deep themselves. They worked from the surface, lowering instruments and interpreting what came back up. The ocean remained, in a sense, invisible. To truly understand it, someone would need to descend into it, to observe the depths firsthand. This dream, as old as the Challenger voyage itself, would take many decades to realize. The challenge was immense. Water pressure increases by 1 atmosphere for every 10 meters of depth. At 1,000 meters, the pressure is 100 atmospheres, enough to crush most structures. At deeper levels, the forces involved are staggering, far beyond what the human body can endure. Any vessel designed to carry people into the deep would need to withstand these pressures while remaining light enough to descend and buoyant enough to return to the surface. Early attempts at underwater exploration focused on shallow waters. Diving bells, simple inverted containers that trapped air when submerged, had been used for centuries to allow workers to labor underwater on bridges, piers, and shipwrecks. But these bells were limited to depths of a few dozen meters at most, and divers inside them breathed air at increasing pressure, which brought its own dangers. In the mid-1800s, engineers began developing diving suits, sealed garments that protected divers and supplied them with air pumped from the surface. Augustus Seebee, a German instrument maker, refined these designs, creating what became known as the standard diving dress. This suit, with its heavy helmet, weighted boots, and air hose, became the iconic image of deep-sea diving. Divers wearing these suits could descend to depths of 100 meters or more, though they faced risks from pressure, cold, and the physical demands of working underwater. But these suits were tethered to the surface, dependent on air pumped down through a hose. They allowed divers to work at moderate depths, but they were not true exploration vehicles. They were tools for specific tasks: salvaging shipwrecks, inspecting underwater structures, recovering lost objects. For deeper exploration, something entirely different was needed. In the late 1800s and early 1900s, inventors began experimenting with submersibles, small vessels that could descend independently, carrying their own air supply and power source. These early designs were crude, often dangerous, and rarely successful. Many sank and never returned. Others leaked, flooded, or lost power at depth. The engineering challenges were formidable, and progress was slow. One of the key innovations came from understanding buoyancy. A submersible needed to be heavier than water to descend, but it also needed a way to become lighter to ascend. Submarines achieved this by flooding ballast tanks to sink and blowing the water out with compressed air to rise. But this method only worked in relatively shallow water. At great depths, the pressure was too high for compressed air to expel the water from the tanks. Engineers realized they needed a different approach. Instead of using air for buoyancy, they could use a liquid that was lighter than water but incompressible. Gasoline fit this requirement perfectly. It floated on water, it didn't compress under pressure, and it could be stored in tanks. By filling a large tank with gasoline and attaching a heavy pressure sphere for the crew, a submersible could descend using ballast weights and return to the surface by dropping those weights, relying on the gasoline's buoyancy to lift it back up. This concept would eventually lead to the development of the bathyscaphe, a deep diving vessel capable of reaching the ocean's greatest depths. But that development took time, and in the meantime, other technologies were advancing. In the early 1900s, sonar was invented, a technology that would revolutionize ocean exploration. Sonar, short for sound navigation and ranging, worked by sending out pulses of sound and listening for the echoes that bounced back from the seafloor or from objects in the water. By measuring the time it took for the echo to return, operators could calculate the distance to the object. This allowed ships to map the seafloor without lowering a sounding line, a much faster and more efficient process. Sonar was initially developed for military purposes to detect submarines and navigate underwater hazards, but scientists quickly recognized its potential for oceanography. With sonar, they could create detailed maps of the seafloor, revealing underwater mountains, valleys, and ridges that had never been seen before. These maps, in turn, raised new questions. Why did the ocean floor have such varied topography? What forces shaped these features? And what did they reveal about the planet's history? In the 1920s and 30s, sonar surveys began to reveal one of the most important geological features on Earth. The mid-ocean ridges, these underwater mountain ranges, stretching for thousands of miles across the ocean basins, were unlike anything on land. They were long, continuous and symmetrical, running down the center of the Atlantic, Pacific and Indian Oceans. At the time, no one understood what these ridges were or how they formed. But their discovery was a clue, a piece of a larger puzzle that would eventually lead to the theory of plate tectonics. Meanwhile, interest in deep-sea diving continued to grow. In the 1930s, an American naturalist named William Beebe became fascinated with the idea of observing deep-sea life in its natural environment. Working with an engineer named Otis Barton, Beebe designed a spherical steel chamber called the bathysphere. It was a simple but effective design. A hollow steel ball with thick walls, small windows made of fused quartz, and a hatch that could be bolted shut. The bathysphere was lowered on a steel cable, and Beebe sat inside, peering out through the windows at the world outside. The first dives took place off the coast of Bermuda in the early 1930s. Beebe and Barton descended slowly, the cable spooling out from a winch on the ship above. As they went deeper, the water changed color, from bright blue to deep indigo to a darkness that seemed almost solid. At around 200 meters, sunlight faded completely, and Beebe switched on a spotlight to illuminate the water outside. What he saw astonished him. Fish swam past the windows, some with bioluminescent organs that glowed softly in the darkness. Jellyfish drifted by, their bodies transparent and delicate. Occasionally, a larger shape would appear at the edge of the light, something too big or too fast to identify, a reminder that the ocean held mysteries still beyond human comprehension. Beebe described these dives in vivid poetic language, writing articles and books that captured the public's imagination. He spoke of the deep as a place of wonder, a frontier as strange and remote as outer space. His words inspired a generation of oceanographers and engineers, planting the idea that the deep ocean was not just a subject for scientific study, but a place worth experiencing firsthand. The bathysphere had limitations. It was tethered to the surface, dependent on the cable for support and communication. If the cable broke, Beebe and Barton would plunge to the bottom and be crushed instantly. The risk was real, and they knew it. But the rewards, the chance to see what no one else had seen, justified the danger in their minds. Over several years, Beebe and Barton pushed the bathysphere deeper and deeper. In 1934, they reached a depth of over 900 meters, a record that stood for many years. At that depth, the pressure on the sphere's hull was immense, but the steel held. The windows creaked and groaned, but they did not crack. Beebe emerged from these dives with a profound respect for the ocean's power and a conviction that humanity's exploration of the deep had only just begun. The bathysphere proved that humans could descend into the deep and observe the ocean firsthand, but it also revealed the limitations of a tethered design. The cable was a lifeline, but it was also a constraint. It limited how deep the sphere could go, how long it could stay down, and where it could explore. To reach the very deepest parts of the ocean, engineers would need to design a vessel that could descend independently, free from any connection to the surface. This challenge was taken up by a Swiss scientist named Auguste Piccard. Piccard was already famous for his high-altitude balloon flights, having set records by ascending into the stratosphere in a pressurized gondola. He understood the principles of pressure, buoyancy, and how to design structures that could withstand extreme environments. And he realized that the same concepts that allowed a balloon to ascend into the thin air of the upper atmosphere could be adapted to allow a submersible to descend into the crushing depths of the ocean. Piccard's design, which he called the bathyscaphe, combined a spherical pressure chamber with a large float filled with gasoline. The gasoline provided buoyancy, while iron pellets in hoppers beneath the float acted as ballast. To descend, the bathyscaphe would take on water and carry the heavy ballast down. To ascend, it would release the ballast, and the gasoline's buoyancy would lift it back to the surface. It was a simple, elegant solution, and it eliminated the need for a cable. The first bathyscape, called the FNRS-2, was completed in the late 1940s. Piccard tested it in shallow waters near the coast of West Africa, and it performed well, descending and ascending as designed. But the vessel was damaged during recovery, and Piccard decided to build a new one, incorporating lessons learned from the first attempt. This second bathyscaphe was named Trist, after the city on the border of Italy and Yugoslavia where it was built. The Trieste was longer and more robust than its predecessor, with a pressure sphere made of thick steel capable of withstanding the pressures at the very bottom of the ocean. Pickard conducted a series of test dives in the Mediterranean, descending to depths of over 3,000 meters and proving that the design was sound. The Trieste attracted attention from the United States Navy, which was interested in developing deep-sea capabilities for both scientific and military purposes. In 1958, the Navy purchased the Trieste and brought it to California for further modifications. The pressure sphere was replaced with an even stronger one, manufactured by the Krupp Steelworks in Germany. This new sphere had walls over 5 inches thick, and it was designed to withstand pressures equivalent to those at the deepest point in the ocean. The Navy's goal was ambitious: to send the Trieste to the Challenger Deep, the deepest known point on Earth, and prove that humans could reach even the most extreme environments on the planet. The mission, called Project Necton, would test the limits of human engineering and courage. In late 1959, the Trieste was transported to Guam, a small island in the western Pacific near the Mariana Trench. The crew spent weeks preparing the vessel, checking and rechecking every system, every seal, every piece of equipment. The margin for error was zero. At the bottom of the Challenger Deep, the pressure would be over 1,000 atmospheres, enough to crush any weakness in the hull. The pilot for the dive would be Jacques Piccard, Auguste's son, who had worked alongside his father on the bathyscaphe's development. Joining him would be Don Walsh, a young U.S. Navy lieutenant and oceanographer. Together they would attempt what no one had ever done: descend nearly 7 miles into the ocean's deepest abyss. Before the dive, the crew needed to locate the exact deepest point. The Challenger Deep was a vast trench, and finding its lowest spot was not straightforward. Depth sounders at the time couldn't measure such extreme depths accurately, so the team used a crude but effective method. They dropped blocks of TNT into the water, lit the fuses, and used stopwatches to time the echoes bouncing back from the seafloor. The longer the delay, the deeper the water. It was a rough measurement, but it worked well enough to give them a target. On the morning of January 23, 1960, the sea was rough, and waves swept over the Trieste's deck as it floated on the surface. Piccard and Walsh climbed down into the pressure sphere, a cramped space barely large enough for 2 people. The hatch was sealed with a single bolt, a heavy steel door that would hold against the pressure outside. Inside, the air was fresh, kept dry by silica gel to prevent condensation. The 2 men settled in, checked their instruments, and gave the signal to begin the descent. The ballast tanks were flooded, and the Trieste began to sink. The motion was gentle at first, the vessel rocking in the waves, but as it descended below the surface, the turbulence ceased. The ocean closed over them, and they entered a world of silence and stillness. The descent was slow, deliberate. Piccard monitored the depth gauge, the pressure readings, the temperature. Walsh kept notes, recording every detail for the mission log. As they sank deeper, the color of the water shifted from blue to green to a twilight gray. At around 200 meters, sunlight faded completely, and they switched on the Trieste's external lights. The lights revealed a constant rain of particles drifting downward, a phenomenon known as marine snow. These particles, made of dead plankton, fecal matter, and organic debris, fell slowly through the water column, feeding the creatures that lived in the depths. It was like descending through a gentle snowstorm, each flake glowing softly in the beam of the lights. Hours passed. The Trieste continued its descent, meter by meter, the pressure outside increasing relentlessly. At around 9,000 meters, they heard a sharp crack. Both men froze, listening. The sound had come from somewhere outside the sphere, perhaps from the float or the support structure. They checked the instruments. Everything seemed normal. The pressure sphere was holding. The crack, they decided, had been the outer plexiglass window breaking under the pressure. It was not part of the pressure hull, just a protective layer, and its failure did not threaten the mission. They continued down. The darkness outside was absolute, broken only by the occasional flash of bioluminescence as tiny creatures reacted to the Trieste's presence. At around 10,000 meters, they began to see the seafloor on their sonar. They slowed the descent, releasing small amounts of ballast to fine-tune their speed. And then, gently, the Trieste touched down. They had reached the bottom of the Challenger Deep, nearly 11,000 meters below the surface. The pressure outside was over 16,000 pounds per square inch, a force almost beyond comprehension. But inside the sphere, Pickard and Walsh were safe, protected by the thick steel walls that surrounded them. They peered out through the tiny windows. The seafloor was soft, covered in fine sediment that had been disturbed by their landing. The water was murky, stirred up by the impact, but as the sediment settled, they could see the bottom more clearly. It was flat, featureless, a vast plain of mud stretching away into the darkness. And then, something moved. Walsh later reported seeing what he believed was a flatfish, a creature swimming near the bottom. The sighting was debated for years afterward. Some scientists argued that fish could not survive at such depths, that the pressure and lack of food made it impossible. Others pointed to the sighting as evidence that life could adapt to even the most extreme conditions. Regardless of whether the creature was truly a fish or something else, the fact remained the bottom of the ocean was not lifeless. Even here, in the deepest, coldest, most pressurized environment on Earth, something lived. Pickard and Walsh stayed on the bottom for about 20 minutes, taking photographs, recording observations, and simply absorbing the fact of where they were. Then, with their time and air running short, they decided to return to the surface. They released the ballast, and the Trieste began to rise, lifted by the buoyancy of the gasoline float. The ascent took several hours, a slow drift upward through the dark. As they climbed, the pressure decreased, the water grew lighter, and eventually, sunlight began to filter down from above. When they finally broke the surface, bobbing in the waves, they climbed out of the sphere and stood on the deck, looking back at the ocean that had just released them from its deepest embrace. The dive to the Challenger Deep was a triumph, proof that human ingenuity could overcome even the most extreme challenges, but it was also a solitary achievement. After 1960, no one returned to the Challenger Deep for over 50 years. The technology was available, but the funding and interest were not. The deep ocean, it seemed, was too remote, too expensive, and too difficult to justify continued exploration. The descent of the Trieste to the Challenger Deep remains one of the most remarkable achievements in the history of ocean exploration. It was a feat of engineering, courage, and patience, accomplished at a time when the technology was still in its infancy and the risks were enormous. To understand what made this dive so significant, it's worth looking more closely at the details, at the vessel itself, the men who made the journey, and the legacy they left behind. The Trieste, as it was configured for the Challenger Deep Dive, was a vessel of contrasts. The float was over 50 feet long, a massive tank filled with gasoline to provide buoyancy. Attached to the bottom of this float was the pressure sphere, a tiny capsule just over 6 feet in diameter. The sphere was the heart of the vessel, the only part designed to withstand the crushing pressure of the deep. Everything else, the float, the hoppers for ballast, the support structures, would be exposed to the pressure, but they didn't need to resist it in the same way. The gasoline in the float was incompressible, so it didn't matter if water seeped into the float's outer structure. The sphere, however, had to remain absolutely watertight. The sphere's walls were made of forged steel, 5 inches thick in places. The material was chosen for its strength and its ability to withstand extreme stress without cracking. There were 3 small portholes, thick cones of plexiglass designed to handle the pressure. The largest porthole, the one that cracked during the descent, was a protective outer layer. The inner cone, the one that actually held the pressure, remained intact. Inside the sphere, space was minimal. Pickard and Walsh sat on small seats, surrounded by instruments, oxygen tanks, and canisters of soda lime to absorb carbon dioxide. The air inside was breathable, but it was recycled, and over the course of the dive, it would gradually become stale and humid. The temperature dropped as they descended, and both men wore warm clothing to ward off the cold. The descent itself was a study in patience. The Trieste sank slowly, averaging about 3 feet per second in the initial stages. Pickard adjusted the rate by releasing small amounts of ballast, using the descent as an opportunity to test the vessel's response and ensure everything was functioning as expected. At deeper levels, he slowed the descent further to just 1 foot per second, giving them time to react if the seafloor appeared suddenly on the sonar. Communication with the surface ship was minimal. The Trieste had an acoustic telephone, a device that used sound waves to transmit speech through the water, but the signal was weak and often garbled by interference. Mostly, Pickard and Walsh were on their own, isolated in their steel capsule, descending into a realm where no one could help them if something went wrong. The moment they touched the bottom was anticlimactic in some ways. There was no dramatic impact, No sudden revelation. The seafloor appeared on the sonar. They slowed the descent, and then there was a gentle bump as the sphere settled onto the sediment. But the significance of that moment was profound. They were sitting on the lowest point on Earth, farther below sea level than Mount Everest is above it. The weight of the ocean pressed down on them, a column of water nearly 11 kilometers tall, and yet they were safe, protected by the strength of the steel sphere. The view outside was limited. The sediment they had stirred up obscured much of the seafloor, and the Triest's lights could only penetrate a few meters into the murky water. But what they could see was enough. The bottom was not a barren wasteland. There was sediment, fine and soft, suggesting slow accumulation over eons. And there was life, or at least something that moved, a reminder that even in the most extreme environments, life found a way. Walsh's reported sighting of the flatfish became a point of controversy. Later analysis suggested that what he saw might have been a sea cucumber or some other invertebrate rather than a true fish. The pressure at that depth, over 1,000 atmospheres, creates physiological challenges that most fish cannot overcome. Their cells, their enzymes, their very biochemistry begins to break down under such conditions. But the debate over what Walsh saw is less important than what the sighting represented. Evidence that the deep ocean, even at its most extreme, was not devoid of life. After their brief time on the bottom, Piccard and Walsh began the ascent. They released the iron ballast, and the Trieste rose, slowly at first, then faster as the pressure decreased and the gasoline expanded slightly. The ascent was smoother than the descent, a gentle drift upward through layers of water that grew progressively lighter and warmer. When they reached the surface, the support ship was waiting. The crew helped secure the Trieste, and Piccard and Walsh climbed out, exhausted but elated. They had done it. They had reached the deepest point on Earth and returned safely. It was a triumph for science, for engineering, and for the human spirit. But the triumph was also bittersweet. The dive to the Challenger Deep had been a one-time event, a proof of concept that was never followed up. The Trieste continued to operate for a few more years, conducting research dives and assisting in the search for the lost submarine USS Thresher, but it never returned to the Challenger Deep. The cost and complexity of such dives, combined with a lack of clear scientific objectives, meant that deep ocean exploration shifted to other methods, other technologies. For over 50 years, Piccard and Walsh remained the only people to have visited the Challenger Deep. It wasn't until 2012, when filmmaker James Cameron descended to the bottom in a specially designed submersible called the Deep Sea Challenger, that another human set eyes on that remote landscape. And even then, Cameron's dive was a solo mission, a brief visit that lasted only a few hours. The Trieste itself was retired in the mid-1960s. The original pressure sphere was removed and used in a new vessel, Trieste the Sink, which continued to serve the Navy for several more years. The original Trieste, stripped of its sphere, was eventually put on display at the U.S. Navy Museum in Washington, D.C., where it remains today, a relic of an era when the deep ocean was the final frontier. While the Trieste's dive to the Challenger Deep captured headlines, a quieter revolution was taking place in ocean exploration. Engineers and scientists were developing smaller, more maneuverable submersibles that could reach moderate depths and stay down for extended periods. These vessels, though they couldn't go as deep as the Trieste, offered something the bathyscaphe did not: the ability to move freely, to explore, to conduct research in a way that a simple up-and-down dive could not. One of the most important of these submersibles was Alvin, developed by the Woods Hole Oceanographic Institution in Massachusetts. Alvin was conceived in the early 1960s, designed to be a versatile research tool that could carry scientists to depths of several thousand meters. Unlike the Trieste, which was massive and slow, Alvin was relatively compact, with a small pressure sphere and external thrusters that allowed it to maneuver precisely. The sphere, made of titanium, could hold 3 people, a pilot and 2 scientists. The titanium was chosen for its strength-to-weight ratio, making the sphere both strong enough to resist pressure and light enough to be buoyant. Alvin had viewports that gave the occupants a clear view of the surrounding water, robotic arms that could collect samples, and external lights that illuminated the seafloor. Alvin became operational in 1964, and it quickly proved its worth. Early dives tested its systems, its maneuverability, and its ability to perform tasks at depth. In 1966, Alvin was used to locate a lost hydrogen bomb off the coast of Spain. The bomb had been lost in a mid-air collision, and it came to rest on the seafloor at a depth of over 2,000 feet. Alvin's crew located the bomb, though initial attempts to recover it caused it to slip deeper. Eventually another vehicle retrieved it, but the mission demonstrated Alvin's capabilities and brought it to the attention of both the Navy and the scientific community. Over the following years, Alvin conducted hundreds of dives, supporting research in geology, biology, and oceanography. It descended to the seafloor to study volcanic features, to collect samples of rock and sediment, and to observe marine life in its natural habitat. The submersible allowed scientists to see the deep ocean in a way that remote instruments never could. They could watch fish swim, observe how currents shaped the seafloor, and make decisions in real time about where to sample and what to collect. Other submersibles were developed around the same time. France built a vessel called Siana. Similar in design to Alvin, the Soviet Union developed the Mirror submersibles, capable of reaching even greater depths. Japan, Canada, and other nations invested in their own deep-sea vehicles, recognizing that the ocean floor held secrets worth exploring. But despite these advances, deep-sea exploration remained expensive and limited. Each dive required extensive preparation, a support ship, a trained crew, and favorable weather. Submersibles could only stay down for a few hours before their batteries ran low or their life support systems needed replenishment, and they could only carry a few people, limiting the number of scientists who could experience the deep firsthand. Still, the submersibles provided invaluable data. They revealed the complexity of the seafloor, the diversity of deep-sea life, and the dynamic processes that shaped the ocean bottom. Geologists used them to study mid-ocean ridges, the underwater mountain ranges where new seafloor was being formed. Biologists used them to observe creatures that had never been seen alive, animals adapted to crushing pressure, near-freezing temperatures, and total darkness. One of the most significant discoveries made from a submersible came in the mid-1970s, during an expedition to the Galapagos Rift, a section of the mid-ocean ridge in the eastern Pacific. Scientists aboard Alvin were exploring the ridge, looking for signs of volcanic activity and studying the geology of the spreading center. What they found was something entirely unexpected, something that would change the way we think about life on Earth. In 1977, a team of geologists and geochemists set out to explore the Galapagos Rift, a section of the mid-ocean ridge located about 400 miles off the coast of South America. The ridge was a spreading center, a place where tectonic plates were pulling apart and new oceanic crust was being formed. The scientists wanted to study the volcanic and tectonic processes that created this new crust, and they hoped to find evidence of geothermal activity on the seafloor. They brought with them a camera system called Angus, which stood for Acoustically Navigated Geological Underwater Survey. Angus was essentially a camera in a protective frame, towed behind a ship and lowered to the seafloor. As it was dragged across the bottom, it took photographs at regular intervals, creating a visual record of the terrain below. When the team reviewed the photographs from Angus, they saw something unusual. In one area, the images showed dense clusters of white clams, far larger than any clams that should have been living at such depths. Deep-sea sediments were typically devoid of large animals, since food was scarce and energy was limited. But here, the seafloor seemed to be teeming with life. Intrigued, the scientists decided to send Alvin down to investigate. On February 17, 1977, Alvin descended to the Galapagos Rift, carrying geochemist Jack Corliss and two other scientists. As they approached the seafloor, the pilot maneuvered the submersible toward the area where Angus had photographed the clams. What they saw astonished them. The clams were real, massive white clams with bright red flesh visible inside their shells. Some were nearly a foot long. They were clustered around cracks in the seafloor, and from these cracks, shimmering water was rising, distorting the view like heat waves on a desert road. Corliss reached out with Alvin's robotic arm and inserted a temperature probe into the shimmering water. The reading came back at about 8 degrees Celsius, much warmer than the surrounding seawater, which hovered just above freezing. They had found a hydrothermal vent, a place where seawater was seeping down through cracks in the oceanic crust, being heated by magma below, and then rising back up, carrying dissolved minerals and chemicals. But the vents themselves, remarkable as they were only part of the discovery. The real revelation was the life surrounding them. In addition to the giant clams, the scientists saw tube worms, some over 6 feet long, waving gently in the current. They saw crabs scuttling across the rocks, mussels clinging to the vent openings, and fish swimming through the warm water. This was an ecosystem unlike any other on Earth. On the surface and in the shallow ocean, life depended on sunlight. Plants used photosynthesis to convert light into energy, and animals ate the plants or each other, forming a food chain that ultimately traced back to the sun. But here, in the deep ocean, there was no sunlight. The vents were miles below the surface, in perpetual darkness, yet life thrived. The explanation came from studying the bacteria that lived in and around the vents. These bacteria did not use sunlight for energy. Instead, they used chemicals, specifically hydrogen sulfide, which poured out of the vents in high concentrations. Through a process called chemosynthesis, the bacteria oxidized the hydrogen sulfide, using the energy released to convert carbon dioxide into organic molecules. The bacteria were the base of the food chain, filling the role that plants played on land or in the sunlit surface waters. The giant clams and tubeworms had evolved symbiotic relationships with these bacteria. The tubeworms, which had no mouth or digestive system, housed billions of bacteria inside specialized organs called trophosomes. The worms absorbed hydrogen sulfide and oxygen from the water and transported it to the bacteria, which in turn produced nutrients that the worms could absorb. It was a partnership, a way of living that had evolved independently of the sun. The discovery of hydrothermal vents and their associated ecosystems was one of the most important biological findings of the 20th century. It proved that life could exist in places and in ways that no one had imagined. It suggested that the early Earth, before photosynthesis evolved, might have been dominated by chemosynthetic organisms living near volcanic vents, and it raised the tantalizing possibility that similar ecosystems might exist on other planets or moons, in places where sunlight never reached but where geothermal energy was available. Over the following years, scientists returned to the Galapagos Rift and explored other vent systems around the world. They found vents in the Atlantic, in the Pacific, and in the Indian Ocean. Each vent system had its own unique community of organisms, adapted to the specific chemistry and temperature of that particular location. They found black smokers, vents that spewed superheated water at temperatures exceeding 350 degrees Celsius, so hot that the dissolved minerals precipitated out instantly, forming towering chimneys of sulfide and other compounds. They discovered worms that could tolerate temperatures that would kill most animals, crabs that farmed bacteria on their claws, and fish that lived on the edge of the vent plumes, feeding on the shrimp and other creatures drawn to the warmth. The diversity was staggering, and new species were being described with every expedition. The vents also had geological significance. They were part of the ocean's circulation system, drawing in cold seawater, heating it, and returning it enriched with minerals. This process, repeated at thousands of vents around the world, played a role in regulating the ocean's chemistry, cycling elements like iron, manganese, and sulfur through the water. The vents were not just isolated curiosities, they were integral to the functioning of the ocean as a whole. For Alvin, the discovery of hydrothermal vents marked the beginning of a new era. The submersible became the primary tool for studying these systems, conducting hundreds of dives to vents around the globe. Scientists from many disciplines, geology, biology, chemistry, even astrobiology, used Alvin to explore, to collect samples, and to unravel the mysteries of these strange, vibrant ecosystems. The vents reminded humanity that the ocean was still full of surprises, that even in the late 20th century, with all our technology and knowledge, there were entire worlds waiting to be discovered. And they underscored the importance of exploration, of going to sea for yourself, rather than relying solely on remote instruments and theoretical predictions. As the 20th century drew to a close, deep ocean exploration was about to undergo another transformation. Manned submersibles like Alvin had proven their value, but they were limited by their need for life support, by the physical and psychological demands of putting humans in such extreme environments, and by the high costs of operation. A new technology was emerging, one that could explore the deep without putting lives at risk: remotely operated vehicles, or ROVs. ROVs were, in essence, underwater robots. They were tethered to a ship by a long cable that provided power and transmitted data. Operators on the surface controlled the ROVs using joysticks and monitors, watching live video feeds from the vehicle's cameras and directing it to move, collect samples, or perform other tasks. The concept was not new. The first ROVs had been developed in the 1960s for military and commercial purposes, but it took decades for the technology to mature and become practical for scientific research. Early ROVs were large, cumbersome, and unreliable. They often lost power, got tangled in their tethers, or suffered equipment failures at depth. But engineers gradually improved the designs, making the vehicles smaller, more robust, and easier to control. By the 1980s, ROVs were being used in the offshore oil and gas industry to inspect pipelines, repair underwater structures, and perform tasks that would be too dangerous or expensive for human divers. Scientists recognized the potential of ROVs for ocean exploration, a vehicle that could stay underwater for hours or even days, that didn't require life support or worry about decompression, and that could be operated from the safety of a ship, offered enormous advantages. And unlike manned submersibles, which could only carry 2 or 3 people, ROVs could be monitored and controlled by entire teams of scientists, allowing for collaborative decision-making and real-time analysis. In the 1990s, several research institutions began developing advanced ROVs specifically for scientific exploration. The Woods Hole Oceanographic Institution built Jason, a sophisticated vehicle equipped with high-definition cameras, manipulator arms, and sensors for measuring temperature, salinity, and chemical composition. Jason was designed to work in tandem with a second ROV called Medea, which absorbed the ship's motion and kept Jason stable, allowing for smooth, precise operations on the seafloor. Jason quickly became a workhorse of deep-sea research. It explored hydrothermal vents, mapped underwater volcanoes, studied deep-sea corals, and collected samples from some of the most remote and inaccessible places on Earth. Because it could stay down for extended periods, Jason allowed scientists to conduct detailed surveys and experiments that would have been impossible with a manned submersible. The Monterey Bay Aquarium Research Institute developed similar vehicles, including the ROV Tiburon, which was used extensively for mid-water and deep-sea research off the coast of California. Tiburon was equipped with specialized tools for collecting delicate organisms, such as jellyfish and other gelatinous creatures that would be damaged by traditional sampling methods. The ROV's manipulator arms could scoop up these fragile animals and place them gently in containers, preserving them for study. Other countries invested in ROV technology as well. Canada developed ROPURS, a vehicle used for deep-sea vent research, and the deployment of ocean observatories. The United Kingdom, Japan, France, and Germany all built their own ROVs, each tailored to specific research needs. The proliferation of these vehicles meant that deep-sea exploration was no longer the exclusive domain of a few wealthy institutions or nations. It was becoming more accessible, more collaborative, and more productive. ROVs also played a crucial role in some of the most high-profile underwater discoveries of the late 20th and early 21st centuries. In 1986, ROVs assisted in the exploration of the wreck of the Titanic, the famous ocean liner that sank in the North Atlantic in 1912. The wreck lay at a depth of nearly 4,000 meters, far beyond the reach of divers but within the range of ROVs. The vehicles captured detailed images of the ship's exterior and interior, revealing the extent of the damage and providing insights into how the ship had broken apart as it sank. The exploration of the Titanic demonstrated the power of ROVs to reach places and document events that had been inaccessible for decades. It also sparked public interest in deep-sea exploration, bringing the mysteries of the ocean into living rooms around the world through documentaries and media coverage. In the early 2000s, ROVs continued to push the boundaries of what was possible. They explored underwater caves, surveyed deep-sea canyons, and documented marine life in previously unexplored regions. They were used to study the impacts of ocean acidification, to monitor the health of deep-sea coral reefs, and to investigate the effects of climate change on deep-sea ecosystems. One of the most exciting developments was the use of ROVs to explore the deepest ocean trenches. Vehicles like Nereus, developed by Woods Hole, were designed to reach depths of 11,000 meters, matching the Trieste's record from 1960. Nereus successfully dove to the Challenger deep in 2009, conducting surveys and collecting samples. Unlike the Trieste, which could only descend and ascend, Nereus could move freely across the seafloor, taking detailed measurements and capturing high-definition video. Tragically, Nereus was lost during a dive in the Kermadec Trench in 2014, likely due to implosion caused by pressure-related failure. But its missions had proven that ROVs could operate at full ocean depth, and work continued on developing even more advanced vehicles. ROVs also enabled new forms of collaboration between scientists and the public. Many research institutions began live streaming ROV dives, allowing anyone with an internet connection to watch as the vehicles explored the deep. Viewers could see hydrothermal vents up close, watch fish swim past the camera, and observe the process of scientific discovery in real time. This democratization of exploration helped to build public support for ocean research and inspired a new generation of scientists and engineers. The ROV revolution did not replace manned submersibles, rather it complemented them. Each technology had its strengths. Manned submersibles offered the immediacy and intuition that came from having a scientist physically present at the site. ROVs offered endurance, safety, and the ability to conduct long-duration missions. Together, they provided a comprehensive toolkit for exploring the ocean's depths. As we move into the 21st century, deep ocean exploration has entered a new phase, characterized by advanced technology, international collaboration, and a growing awareness of the ocean's importance to the planet's health. The tools available to researchers today are more sophisticated than ever, and the pace of discovery has accelerated. Yet the ocean remains in many ways as mysterious as it was in the days of the HMS Challenger. One of the most significant developments in recent years has been the advent of autonomous underwater vehicles, or AUVs. Unlike ROVs, which are tethered to a ship, AUVs operate independently, following pre-programmed routes and making decisions based on onboard sensors and artificial intelligence. AUVs can map the seafloor, collect water samples, and even search for specific features like hydrothermal vents or shipwrecks, all without direct human control. AUVs are particularly useful for surveying large areas. They can operate for hours or even days, covering hundreds of miles and gathering data that would take weeks or months to collect using other methods. The maps they produce are incredibly detailed, revealing the ocean floor's topography with a resolution that was unimaginable just a few decades ago. These maps have led to new discoveries. Sepamounts, underwater volcanoes that rise thousands of feet from the seafloor, have been found in remote regions of the ocean. Deep sea canyons, some rivaling the Grand Canyon in size, have been mapped and studied, and new hydrothermal vent fields continue to be discovered, each one adding to our understanding of how these systems function and how they support life. Another important development has been the use of deep-sea landers, autonomous platforms that descend to the ocean floor and remain there for extended periods, collecting data on temperature, pressure, currents, and biological activity. Landers are often equipped with cameras, bait to attract scavengers, and traps to capture small organisms. They provide a window into the deep-sea environment, showing how it changes over time and how animals behave when no humans are present. Landers have been deployed in some of the deepest ocean trenches, including the Mariana Trench, the Kermadec Trench, and the Japan Trench. They have captured footage of fish, amphipods, and other creatures living at depths previously thought to be too extreme for complex life. Some of these organisms are new to science, species that have never been seen before, and that are adapted to pressures and temperatures that few other animals could tolerate. In 2012, filmmaker and explorer James Cameron descended to the Challenger deep in a specially designed submersible called the Deep Sea Challenger. The dive was a solo mission, with Cameron alone in the pressure sphere, and it was the first time a human had visited the Challenger deep since Pickard and Walsh's dive in 1960. Cameron spent several hours on the bottom, collecting samples and filming the landscape. His footage provided the first high-definition images of the deepest point on Earth, revealing a barren but strangely beautiful terrain of fine sediment and scattered rocks. Cameron's dive was followed by other deep-sea missions. In 2019, explorer Victor Vescovo descended to the Challenger deep in a submersible called the Limiting Factor, and he has since returned multiple times. Vescovo's vehicle is part of the 5 Deeps expedition, a project to visit the deepest point in each of the world's 5 oceans. The expedition has successfully reached all 5 deeps, collecting data and samples from places that had never been explored before. These modern dives are made possible by advances in materials, science, engineering, and navigation. The pressure spheres are made from titanium alloys that are both strong and lightweight. The vehicles are equipped with sophisticated sonar, cameras that can operate in near-total darkness, and manipulator arms that can collect samples with precision. They represent the culmination of decades of engineering effort, refining the designs pioneered by Pickard and Barton, and improving on every aspect of deep-sea exploration. But technology alone is not enough. Modern ocean exploration also depends on international collaboration. The ocean is a global commons, and understanding it requires cooperation between nations, institutions, and disciplines. Projects like the Census of Marine Life, a 10-year effort to catalog the diversity of ocean life, brought together scientists from over 80 countries. They shared data, coordinated expeditions, and built a comprehensive database of marine species that is still being used today. Climate change has added urgency to ocean exploration. The deep ocean plays a critical role in regulating the Earth's climate, absorbing carbon dioxide from the atmosphere, storing heat, and driving global ocean currents. But the deep ocean is also vulnerable to changes in temperature, chemistry, and circulation. Understanding how these changes are affecting deep-sea ecosystems is essential for predicting the future of the planet. Researchers have found that warming surface waters are affecting the deep ocean, altering currents, and changing the distribution of nutrients. Ocean acidification, caused by the absorption of carbon dioxide, is affecting the chemistry of deep-sea sediments and the organisms that live there. And plastic pollution, once thought to be confined to the surface, has been found even in the deepest ocean trenches, a stark reminder of humanity's impact on the planet. Deep-sea mining has also become a topic of intense debate. The polymetallic nodules discovered by the Challenger expedition, those potato-sized lumps of metal, are now seen as a potential resource. They contain valuable minerals like manganese, nickel, and cobalt, which are used in batteries, electronics, and other technologies. Several companies have expressed interest in mining these nodules, but the environmental impacts are not well understood. Disturbing the seafloor could destroy ecosystems that have taken millions of years to develop, and the consequences could ripple through the entire ocean. Scientists are working to understand these impacts before mining begins. They are using ROVs, AUVs, and landers to study the organisms that live on and around the nodules, to measure how sediment plumes from mining operations might spread, and to assess the resilience of deep-sea ecosystems to disturbance. The goal is to inform policy decisions, to ensure that any exploitation of deep-sea resources is done responsibly and sustainably. The deep ocean also holds potential for new medicines and biotechnologies. Many deep-sea organisms produce unique chemicals to survive in extreme conditions, and these chemicals could have applications in medicine, industry, and agriculture. Enzymes from deep-sea bacteria, for example, can function at high temperatures and pressures, making them useful for industrial processes. Compounds from deep-sea sponges and corals have shown promise as antibiotics, antivirals, and anti-cancer agents. But discovering these compounds requires exploration, careful collection of samples, and rigorous testing. It also requires a commitment to protecting the ecosystems from which these organisms come, ensuring that they are not overexploited or destroyed in the pursuit of profit. As technology continues to advance, the future of deep ocean exploration looks promising. New submersibles are being designed with greater depth capabilities, longer endurance, and more sophisticated instruments. ROVs and AUVs are becoming smarter, able to operate with greater autonomy and make decisions based on the data they collect. And new sensors are being developed that can detect and measure things that were previously invisible, from trace chemicals to minute changes in temperature. There is also growing interest in using artificial intelligence and machine learning to analyze the vast amounts of data being collected from the ocean. AI can identify patterns, detect anomalies, and even discover new species from images and video footage. This could accelerate the pace of discovery and allow researchers to focus their efforts on the most interesting and important findings. The ocean, despite all the exploration and discovery of the past century and a half, remains largely unknown. We have mapped more of the moon's surface than we have of our own seafloor. We have sent probes to distant planets, but vast regions of our own ocean remain unexplored. The deep ocean is still a frontier, a place of mystery and wonder, and the journey to understand it has only just begun. The exploration of the deep ocean has also led to discoveries that touch on one of humanity's oldest questions. Are we alone in the universe? The finding that life could exist at hydrothermal vents, in complete darkness, sustained by chemical energy rather than sunlight, fundamentally changed how scientists think about the possibility of life on other worlds. If life could thrive in the deep ocean, in conditions so extreme and so different from the surface, then perhaps it could exist in the subsurface oceans of Europa, one of Jupiter's moons, or Enceladus, a moon of Saturn. Both of these moons are covered in thick ice, but beneath that ice, scientists believe there are vast oceans of liquid water. And where there is liquid water, and where there might be volcanic or tectonic activity providing heat and chemical energy, there could be conditions similar to Earth's deep-sea vents. The discovery of vent ecosystems on Earth has given astrobiologists a template, a model for what life might look like in places we once thought were too hostile to support it. This connection between deep-sea exploration and the search for extraterrestrial life has brought new funding and attention to ocean research. Space agencies like NASA have invested in deep-sea expeditions, using them as analogues for missions to icy moons. Engineers test underwater vehicles in Earth's oceans, preparing for the day when similar vehicles might be sent to explore the oceans of Europa or Enceladus. The deep ocean has also inspired new thinking about the origins of life on Earth. Some scientists now believe that life may have first emerged at hydrothermal vents, where the chemical energy and mineral-rich environment provided the building blocks and the energy needed for the first primitive cells to form. The vents offer protection from the harsh conditions on the early Earth's surface, from ultraviolet radiation, asteroid impacts, and extreme temperature fluctuations. In the stable, energy-rich environment of a vent field, life could have taken hold, evolved, and eventually spread to other parts of the ocean, and eventually to land. These are theories, not proven facts, but they are grounded in the observations made by submersibles and ROVs over the past several decades. Every dive to a vent field, every sample of vent fluid, every organism collected and studied adds to the body of evidence, helping scientists piece together the story of how life began and how it adapted to survive in Earth's most extreme environments. Beyond the purely scientific discoveries, deep ocean exploration has also revealed the interconnectedness of all parts of the ocean system. The deep ocean is not isolated from the surface. Currents move water from the depths to the shallows and back again, a process that takes hundreds or even thousands of years, but that is essential for distributing heat, nutrients, and oxygen around the planet. The deep ocean absorbs carbon dioxide from the atmosphere, helping to moderate the greenhouse effect. It stores vast amounts of heat, acting as a thermal buffer that influences weather patterns and climate. But this interconnectedness also means that the deep ocean is vulnerable to changes happening at the surface. Warming temperatures are affecting the strength and direction of ocean currents. Ocean acidification, caused by the absorption of carbon dioxide, is changing the chemistry of deep-sea sediments and affecting the organisms that depend on calcium carbonate to build their shells and skeletons. Pollution, from plastic debris to chemical contaminants, is finding its way into even the most remote parts of the deep ocean. Researchers have found plastic bags and bottles at the bottom of the Mariana Trench, over 10,000 meters below the surface. They have detected microplastics, tiny fragments of degraded plastic, in the tissues of deep-sea fish and invertebrates. These findings are sobering reminders that human activity, even activity thousands of miles away and thousands of meters above, can impact the deep ocean. Understanding these impacts is one of the most important challenges facing ocean science today. It requires not just exploration but also long-term monitoring, the ability to track changes over time, and to understand how the deep ocean is responding to the pressures we are placing on it. This is where technologies like autonomous underwater vehicles and deep-sea observatories come in. Ocean observatories are networks of sensors placed on the seafloor, connected by cables that provide power and data transmission. These observatories can monitor temperature, pressure, currents, seismic activity, and biological activity continuously, 24 hours a day for years on end. They provide a window into the deep ocean that is always open, capturing events that would be missed by occasional expeditions, such as underwater earthquakes, volcanic eruptions, or sudden blooms of deep-sea life. One such observatory is the Ocean Observatories Initiative, a network funded by the National Science Foundation that includes sites in the Atlantic and Pacific Oceans. These sites are equipped with instruments that measure everything from water chemistry to the sounds made by marine mammals. The data is transmitted to shore in real time and made available to researchers around the world, allowing for collaborative analysis and rapid response to unusual events. Another important tool is satellite oceanography, which, while not directly exploring the deep, provides crucial context for understanding ocean dynamics. Satellites can measure sea surface temperature, ocean color, which indicates the presence of phytoplankton, sea level, and even the shape of the ocean surface, which can reveal the presence of underwater features like seamounts or currents. By combining satellite data with information from deep-sea instruments, scientists can build comprehensive models of how the ocean works from the surface to the seafloor. The future of deep ocean exploration will likely involve even greater integration of technologies. Swarms of small autonomous vehicles working together could map large areas quickly and efficiently. Artificial intelligence could analyze video and sensor data in real time, identifying interesting features and guiding vehicles to investigate further. Advances in battery technology could allow vehicles to stay underwater for weeks or months, conducting long-duration missions that were previously impossible. There is also growing interest in developing underwater habitats, structures where scientists could live and work on the seafloor for extended periods. These habitats, similar in concept to the International Space Station, would allow for continuous observation and experimentation, providing insights that cannot be gained from brief visits in submersibles. Several experimental habitats have been tested over the years, including Aquarius, an underwater laboratory located off the coast of Florida that has been used for research and training. Living underwater presents unique challenges, from the physiological effects of pressure to the psychological demands of isolation and confinement. But it also offers unique opportunities, the chance to observe the ocean on its own terms, to watch how ecosystems change over days and weeks, to conduct experiments that require precise timing and repeated observations. As technology advances, and as our understanding of the ocean deepens, the line between exploration and stewardship becomes increasingly blurred. We are no longer just exploring the ocean, we are also responsible for protecting it. Every discovery brings with it a responsibility to ensure that what we have found is preserved for future generations. This is particularly true in the deep ocean, where ecosystems are fragile and slow to recover from disturbance. Deep-sea corals, for example, grow incredibly slowly, sometimes adding just a few millimeters per year. A coral colony that is hundreds or thousands of years old can be destroyed in seconds by a trawling net or a piece of mining equipment. Once destroyed, it may take centuries or millennia to recover, if it recovers at all. Protecting the deep ocean requires international cooperation and strong governance. Much of the deep ocean lies in international waters, beyond the jurisdiction of any single nation. The United Nations Convention on the Law of the Sea provides a framework for managing these areas, but enforcement is difficult and regulations are often weak. There is ongoing debate about how to balance the desire for resource extraction, whether fishing, mining, or oil and gas drilling, with the need to protect biodiversity and ecosystem function. Some scientists and conservationists are calling for large areas of the deep ocean to be designated as marine protected areas, where extractive activities are prohibited or strictly regulated. These protected areas would serve as refuges for deep-sea life, places where ecosystems can function without human interference. They would also serve as baselines, allowing scientists to compare protected and unprotected areas and to measure the impacts of human activity. Creating such protected areas requires detailed knowledge of what exists in the deep ocean, which in turn requires exploration. This is one of the driving forces behind current expeditions to document what is there before it is lost, to create a record of deep-sea biodiversity that can inform conservation decisions. The deep ocean, for all its remoteness, is not separate from the rest of the planet. It is part of a single, interconnected system, and what happens in the deep affects the entire Earth. The currents that originate in the deep ocean influence climate patterns on land. The organisms that live in the deep play roles in global nutrient cycles, helping to regulate the chemistry of the atmosphere and the ocean. The discoveries made in the deep, from new species to new ecosystems, to new insights into the origins of life, enrich our understanding of the natural world and our place within it. And so we've drifted through the long, patient story of how humanity learned to descend into the deep, from the earliest soundings with weighted ropes to the Challenger's global expedition, from the bathyscaphers that touched the ocean's deepest point to the ROVs that now roam the seafloor like mechanical explorers. The journey has been one of persistence, curiosity, and a refusal to accept that any part of our world should remain unknown. What stands out across all these stories, across all these decades and centuries, is the patience required. Ocean exploration is not fast. It is not dramatic in the way we often imagine exploration to be. It is slow, methodical work, often tedious, sometimes dangerous, but always driven by the quiet conviction that understanding the ocean matters, that what lies beneath the waves is worth the effort, the cost, the risk. The deep ocean has revealed itself to be far more complex, more alive, and more important than anyone in the 19th century could have imagined. It is not a barren desert, but a landscape as varied as any continent, full of mountains, valleys, plains, and features unlike anything on land. It is not lifeless, but teeming with organisms adapted to extremes, thriving in places where life was thought impossible. It is not separate from the rest of the planet, but intimately connected to the climate, the chemistry, and the health of the Earth as a whole. And yet, for all we have learned, the ocean remains mostly unexplored. Most of the seafloor has never been seen by human eyes or even mapped in detail. Most of the species that live in the deep have never been catalogued. Most of the processes that shape the ocean, from the flow of deep currents to the cycling of nutrients through hydrothermal vents, are only partially understood. This is not a failure. It is an invitation. The ocean is still a frontier, still full of mysteries waiting to be uncovered. Every dive, every sample, every measurement adds to the picture, but the picture is far from complete. There are trenches deeper than we have explored, seamounts we have never visited, and ecosystems we have never studied. There are creatures out there, drifting in the dark, that no one has ever seen. There are stories written in the sediment, in the chemistry of the water, in the slow dance of currents, that we are only beginning to read. The tools we have now, the submersibles, the ROVs, the AUVs, the sensors, are more sophisticated than anything available to the Challenger expedition or the Trieste, but the spirit is the same. The desire to know, to understand, to see for ourselves what lies beneath the surface. That spirit, more than any technology, is what has driven ocean exploration forward. As you rest tonight, as your thoughts drift and your breathing slows, you can take comfort in knowing that out there, somewhere on the ocean, a ship is sailing. On board, scientists are preparing for a dive, lowering a vehicle into the water, descending into the dark. They are following a tradition that stretches back over a century, a tradition of patient, careful exploration. They are adding to the story, discovering new chapters, new wonders. The ocean is vast, and it is deep, and it holds more than we can ever fully grasp. But we keep trying, keep descending, keep exploring. Because the ocean is part of who we are. It covers most of our planet. It shapes our climate, provides our food, and holds the memory of our planet's history. Understanding it is not just a scientific endeavor. It is a way of understanding ourselves, our place on this small blue world. And so the journey continues. The deep ocean waits, patient and silent, ready to reveal its secrets to those willing to descend into the darkness and listen to what the water has to say. Sleep well, knowing that the exploration goes on, that the mysteries endure, and that somewhere in the deep there are still wonders waiting to be found.